When a wave travels through a medium, it displaces the particles of the medium from their undisturbed positions. Suppose that a particle is located at a distance x from a coordinate origin. We would like to know the displacement y of this particle from its undisturbed position at any time t as the wave passes. For periodic waves that result from simple harmonic motion of the source, the expression for the displacement involves a sine or a cosine, a fact that is not surprising. After all, harmonic motion is described using sinusoidal equations, and the graphs for a wave on a string look a lot like a plot of displacement versus time for an object oscillating on a spring. Our approach will be to present the expression for the displacement and then show graphically that it gives a correct description. The displacement of a particle caused by a wave traveling in the positive x direction to the right, with an amplitude a, frequency f, and wavelength lambda, is given by y equals a sine 2 pi ft minus 2 pi x divided by lambda. A wave moving in the negative x direction to the left is given by y equals a sine 2 pi ft plus 2 pi x divided by lambda. These equations apply to transverse or longitudinal waves and assume that y equals 0 meters when x equals 0 meters and t equals 0 seconds. The term 2 pi ft plus or minus 2 pi x divided by lambda in these equations is called the phase angle of the wave. In either case, the phase angle is measured in radians, not degrees, so you should be sure to set your calculator to radians mode if calculating any values. Consider a transverse wave moving in the positive x direction along a string. A string particle located at the origin, x equals 0 meters, exhibits simple harmonic motion with a phase angle of 2 pi ft. That is, its displacement as a function of time is y equals a sine 2 pi ft. A particle located at a distance x also exhibits simple harmonic motion, but its phase angle in the upper equation is 2 pi ft plus 2 pi x divided by lambda, which equals 2 pi f times t minus x divided by f lambda, which equals 2 pi f times t minus x divided by v. The quantity x divided by v is the time needed for the wave to travel the distance x. In other words, the simple harmonic motion that occurs at x is delayed by the time interval x divided by v compared to the motion at the origin. Consider the displacement y plotted as a function of position x along the string as the time is incremented by successive intervals of 1/4 of the period, t equals 0, 1/4 t, 1/2 t, 3/4 t, and t. These graphs are constructed by substituting the corresponding value for t into the equation for a wave moving in the positive x direction, remembering that the frequency is equal to 1 divided by the period, and then calculating y at a series of values for x. The graphs are like photographs taken at various times as the wave moves to the right. For reference, the colored square in each graph marks a place on the wave that is located at x equals 0 meters when t equals 0 seconds. As time passes, the colored square moves to the right along with the wave. The usefulness of a mathematical description of a wave is apparent when we want to find the displacement of a particle on the wave at a given time or x position. However, the mathematical description is of great utility when we want to add or subtract waves that overlap in some region, such as in the case of the superposition or interference of waves, topics that we will encounter later.